Okay, so yesterday we were looking at some uh, derivatives of the hyperbolic functions. You know, no light in here. It's starting to get mildly dark. All right, so yesterday we were looking at our hyperbolic functions and the derivatives of hyperbolic functions. Here we left off, I believe, with the hyperbolic, the derivative of the hyperbolic tangent. And we take the derivative of this function, dy dx. You take the derivative of the first multiplied by the second, and then the derivative of the second multiplied by the first. And that's our power rule. And this is what we end up with. We end up with 1 minus the tangent squared, hyperbolic tangent squared of x. But if we look at this, and if we look at this carefully, we have the cosh squared x minus sinh squared of x, and that's equal to e to the x minus plus e to the minus x squared, so that's on 4, minus e to the x minus e to the minus x squared on 4. That's not a very good 4. And we expand that out. We have e to the 2x minus plus 1 plus e to the minus 2x minus e to the 2x. And this is, there are two of them. Let's see, I'm getting a little too far ahead of myself. I got to expand these properly. All right, got to expand that one out. That's e to the x times plus e to the minus x times e to the x plus e to the minus x, and that's equal to e to the 2x plus 1 plus 1 plus e to the minus 2x. All right, so that's the first one expanded on top of 4. On top of 4 minus, now this is e to the x minus e to the minus x squared. That's e to the 2x minus 1 plus e to the minus 2x. So that's minus e to the 2x minus 1 plus e to the minus 2x on 4. That's what that is. And these, now we can start canceling out. So we go there, that's negative, positive, and negative. So that cancels with that cancels with that. These equal to 4 on 4 equals to 1. So now it's like the analog to cosine squared theta plus sine squared theta equals 1. It's the hyperbolic equivalent. So when we have this, we have that's equal to 1. So cos squared x minus sinh squared x is 1. And so, let's see, make sure we're still being captured. All right. Now, if we divide by cos squared x minus cos squared x equals cos squared x, and that's secant squared of x. All right, so that's 1 minus tan squared x equals sec x squared. So now we've got this is equal to sec squared x. And that's where we left it off yesterday. I just wanted to go through that a little bit more detailed because in the video that I went through yesterday, I just left it at this, just assuming that was the right relationship. But I had to go through it to show you that it was the right relationship. So we've got the derivatives now of 3 of the important hyperbolic functions. We could always do the inverse hyperbolic functions. Well, not inverse. The y equals secant or sec x equals 2 on e to the x plus e to the minus x, which is 2 times e to the x plus e to the minus x to the negative 1. So dy dx equals d dx of 2 e to the x plus e to the minus x to the negative 1. That's equal to minus 2 times e to the x plus e to the minus x to the negative 2 times e to the x minus e to the minus x. And then that's equal to minus, all right, we've got e to the x minus e to the minus x on e to the x plus e to the minus x. And this is 2 times 1 on e to the x plus e to the minus x. And this is equal to minus 2. You can put the 2 on that. 2. So we got minus. And that is the tan of x times the sec of x, and that's dy dx. Okay, you can do the same for the cosecant, and so you have all of these neat relationships. Let's take a look at more of the hyperbolic functions and some of the differences, different things that come out of them. the hyperbolic trigonometric functions, that is. So why don't we first look at y equals ln x, e to the y equals x. Whoops, e to the y. So we use the chain rule, d, dy, dy, dx is equal to d dx. So we go d, dy, e to the y, dy, dx equals d, dx of x. And that's equal to 1. d dy of e to the y is e to the y, dy dx. But e to the y is x, so we have x dy dx equals 1, and dy dx equals 1 over x. That's pretty cool. Now that we know that, we can do some little mix and match on some of these impress your friends sort of thing. Show them that you can take these really difficult derivatives. Okay, so y in this case equals a arc sine of x. All right, we get rid of that arc sine. We just take the sine of y equals sine of a sine of x, and that's equal to x, the argument. And then we apply the chain rule. d, dy, dy, dx equals d dx. So here we go, d dy of sine y dy dx equals d dx of x, and that's equal to 1. Now here we got a very important part, and this is critical to any time we take the derivative of an arc, one of the arc trigonometric functions, no matter what it is. The inverse trigonometric functions, you need to take a look at this step right there. You say sine of y. So you take a little right triangle and you say the sine of y is x. Well, the sine of y is x over the hypotenuse, and then use the Pythagorean theorem, and you got 1 minus x squared down there. So d dy of sine of y is cosine of y, dy dx equals 1. But the cosine of y is this over 1. So we have 1 minus x squared dy dx equals 1. dy dx then equals 1 over 1 minus x squared. And that's your derivative of the arc sine. We do the same thing for the cosine function. I know I did this. It doesn't hurt to repeat. Sometimes it's good to do it a couple of times. That way you get the you get to see the flow of it rather than me just trying to figure it out. Okay, so we got y equals a cosine of x. And I use a again, mainly because when you say cos, these two are equivalently read, but that could also be cosine of x to the -1 power, which would be 1 over the cosine of x, which is not at all what the inverse function is. So it's unfortunate that they use this nomenclature, or whatever you want to call it, for arcsines, but they did, and that's something to be careful about. So again, we get x to isolate itself by taking the cosine of y equals the cosine of the arc cos of x, and that's equal to x. So here we go. We got cosine of y equals x. This is that point now where it's a very important point at which we've got to stop and look. And we got x over 1. The cosine of x, or cosine of y, is x, and then that side's going to be 1 minus x squared, according to the Pythagorean theorem. And now you apply the chain rule, d dy cos y dy dx equals d dx of x equals 1. And this is the minus sine of y dy dx equals 1. Now the sine of y is this over that. So we've got minus 1 minus x squared dy dx equals 1. dy dx equals minus 1 over 1 minus x squared. And there you go. That's the derivative of the the inverse cosine. Now we're going to start getting a little cool. We're going to get into some other stuff. Let's do the tangent and secants, and then we're going to start mixing stuff up. So we got y equals the arctan of x, tangent y equals x. I hope by now this step is intuitive. Just taking the tangent of both sides. And now you apply the chain rule, d dy of tangent y equals d dx of x equals 1. Now remember, this is our crucial step here. So we draw our right triangle, and we've got y, and tangent x, so that's sine over the cosine, and this is 1 plus x squared. Okay, so now we got to take the derivative of the tangent of y. Well, let's see. We've got sine x, or let's say we'll just do sine theta over the cosine of theta. Let's see, that's q dq d theta equals the derivative of the first times the second times the derivative of the second times the first. So we got cosine theta cos -1 theta minus sine theta cos -2 theta minus sine theta, but that makes that a positive, and we end up here with 1 plus, and this is tangent squared theta. Well, cosine squared theta plus sine squared theta equals 1. And we have 1 plus tangent squared theta equals secant squared theta. So we end up with this derivative being the secant squared of y equal dy dx equals 1. And it's all bookkeeping. The principles aren't that hard. It's being careful, and often that's my problem, is that I'm not careful. Okay, so we have the tangent y of x. So we got our, so a secant is now the cos of y would be equal to 1 over 1 plus x squared. So secant of y would be equal to 1 plus x squared. And secant squared would be 1 plus x squared dy dx equals 1. dy dx equals 1 over 1 plus x squared. And that's our derivative of the arctan. It starts getting fun at this point because you're working through the problem. You don't have to memorize anything. You work through it. You use your basic knowledge. You use your fundamental knowledge of trigonometry, of some of the things that we learned, the basic derivatives. And we don't even have to memorize anything except a couple of items that remain in our mind, and then we apply them. So now here we go. We got y equals the secant, arcsecant of x. So the secant of y equals x. That's the important part right there. We got it, y. Okay, so then remember the cosine of y would be 1 over x. So that would be 1 and x there. And this would be x squared minus 1. Because you got a, b, and r. A squared plus b squared equals r squared. Now r is x squared. A is 1 plus b squared. So b equals x squared minus 1. All right, so we've got that worked out. Pythagorean theorem. Okay. So now we do the chain rule. D, dy, secant y, dy, dx equals 1. I'm not just going to write d dx of x again. We know it's just 1. So the secant is cosine to the negative 1 power. So dy of cosine y to the negative 1 dy dx equals 1. Don't need that. That's equal to negative cosine y to the negative 2 times negative sine y. dy dx equals 1. And so we end up with negative tangent y let's see, times secant y dy dx equals 1. Okay, so tangent y is minus 1 x squared minus 1, and this is x. Dy dx equals 1. So dy dx equals minus 1 over x times x squared minus 1. That's pretty wild. I think that's so cool. So, and we can do cosecant. I think this is fun. When you get down to it, I think it's beautiful how you can get these relationships. Now we have y equals cosecant, arc cosecant of x. Remember, the cosecant is 1 over the sine of x. Just for memory's sake. So, cosecant of y equals x. I hope that's obvious now. So, our important step, y. Now, the sine of y, 1 over the sine of y equals x. So, we got x here, 1, and this is x squared minus 1 down there. This is the step that you really need to be careful. You have to watch yourself. You don't want to slip up there. So this is now d dx times, I'm skipping I've skipped a couple of steps there just to save time. I think they're trivial at this point, the moot. So we got minus sine y negative 2 cosine of y dy dx equals 1. This is equal to cotangent, negative cotangent y times cosecant of y. Oops, I got a phone call. Just hang on a second. Hello? Hello?
Dear AT&T.
I hate that. dy dx equals 1. But the cotangent of y, now, this is pretty cool. Cotangent of y is x squared minus 1 over 1. So that's minus x squared minus 1. Cosecant of y is x. dy dx equals 1. dy dx equals minus 1 over x squared minus 1. And that's it. The only one left is the cotangent. We haven't done that. And that, you can imagine, is not too different from the tangent, except that we got the sines and the cosines inverted. So, do we do it? Yeah, why not? Why not do it? This way you have it, the whole litany of trigonometric functions. Y equals arc cot of x, and cotangent y equals cotangent arc cot. I'm going to go through the whole thing. X equals cotangent y equals x. And then we have dy, whoops, sorry, dy cotangent of y dy dx equals d dx of x equals 1. And now we got to go to that critical step, which we bypassed. Cotangent of y equals x. So we got 1. And the cotangent is x over 1, or y over x. Remember, or x over y. If this is y and that's x, y over x is the tangent. And just the opposite, x over y, is the cotangent. So this is 1 plus x squared. Okay. So now I have dy of cosine of y times to the negative 1. That's not an arc sine. Dy dx equals 1. This is minus sine of y sine negative 1 of y minus cosine of y sine y, the negative 2, times cosine, cosine of y, and that is equal to 1. Oh, dy dx. dy dx. All right, so this is minus 1 minus cotangent squared y dy dx equals 1. And this is minus cosecant squared of y dy dx equals 1. Now the cosecant squared, that's this over that squared, so that's minus 1 plus x squared dy dx, and dy dx is equal to 1 minus 1 over 1 plus x squared. And that's all she wrote for the trigonometric functions. So we've done every one of them. Okay, I like to be able to see what I'm doing here. Okay. There we go. And you can see the whole board now. Down here. That's our derivative. Sorry about that. That's why I have to have the screen on, because without it, I don't see what you're seeing. Okay, I hope we didn't screw up too much with the others. But you can see this one. Alrighty, now we're going to get into some pretty interesting stuff here. Here, we're going to combine functions. Now, we're going to say, whoops, this is the wrong one. Okay, y equals 1 over x times the arc sine of x. And we want the derivative of that. What is that? Well, we know the derivatives of both of those from our previous rules, our previous application of the chain rule. So why don't we just go to dy dx. I mean, I could make it a little tougher. I could raise. No, it wouldn't work. It wouldn't work. But we know these. So this is d dx of 1 over x times the arc sine of x. And so that is equal to ln x arc sine of x plus 1 over x. And the arc sine of x was 1 over, what was that, 1 minus x squared? I think it was 1 minus x squared. So that would be that derivative. Let me just check and see if I got the right signs. Yeah, that's it. Okay, so basically we just used the power rule we learned the other day. You take the derivative of the first times the second, derivative of the second times the first. And that's what this is. I didn't write that very neatly, so let's rewrite it. That's the natural log of x times the arc sine of x plus 1 over x times the square root of 1 minus x squared. That's a little easier to read than this. Okay, now we got another one. Got a few pretty cool ones. If you can do these on your own, you can do just about any derivative thrown at you. Okay. That was 6, 7. Okay, that was number 8. Here we go, number 9. Number 9 is the same one except cosine. So f of x equals y equals 1 over x cosine, arc cosine of x. So dy dx equals d dx 1 over x times the arc cosine of x. And that's equal to the ln of x times the arc cosine of x plus 1 over x. And I think what was our thingy here? Yeah, it's yeah, times, we gotta make that a minus sign, 1 over 1 minus x squared. And that's dy dx. Not so bad yet. Let's look at something even more interesting. Let's look at another way of applying the chain rule. Let's look at y equals arctangent of e to the x. Well, we can say here that we have the arctangent of u. And we know what to do with that. So we say u is equal to e to the x, and then du dx is equal to e to the x. So we go dy dx equals d du arctangent of u du dx. Now, we've already done the arctangent of the derivative of the arctangent of u, which is 1 over 1 plus u squared du dx. But du dx is e to the x, so we have e to the x over 1 plus e to the x squared, which is 2x. So that's dy dx. Now that's pretty interesting. That's really different. So that is pretty cool stuff. Now that was, we took a look at it. There we go. And that's the problem. That's the solution. We're moving through these pretty quickly. Like I said, if you can do these, you can do just about anything. We've taken a look at an awful lot of functions already and their derivatives. So why don't we look at this one? This one's pretty cool. Let's say y equals the arctangent of x to the third. Well, we do what we did in the previous problem. We say that y equals the arctangent of u, because we know what to do with that. But in this case, u equals x to the third. So there, du dx equals 3x squared. So dy dx equals d du arctangent of u du dx. Now, we already did the arctangent. That was, what was that? That was 1 over u squared. 1 over 1 plus u squared du dx. And that's equal to, so what's u? U is x to the third. So we have 1 plus, alrighty, u, or x to the 6, because x squared, alright, we have u squared, well, u is x to the third squared, so that's equal to x 2 times 3 equals x to the 6. We're going back to our understanding of exponents and the rules of exponents. So x to the 6 times du dx, so we have 3x squared. And we can neaten it up, 3x squared over 1 plus x to the 6. And that's dy dx. Pretty wild. You would never have guessed that this was the derivative of that. It's just pretty neat stuff. You can go on and on. And well, that looks like it for the set of problems that I copied down. So why don't we take a look at something else? Another use of derivatives. So let's take a look at this other use of derivatives. Like I said a couple videos ago, derivatives can help us understand plotting and how to to do a plot. So if we have a function, let's say a polynomial function, let's say x to the third plus 2x squared minus 9. If we try to plot that, we could always set up a table. We go y. Let's see, we can go x and y, and x is 0. Well, let's start in the negatives. X is negative 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. And this would be 4 to the third, so that's 16 times 4, that's 24. That's 64. 64 plus, okay, 16 times 2 is 36 minus 9. Okay, so that's 100. And 100 minus 9, that's 91. So that's 91. Okay, now minus 3. Well, what did I do? That's that should be negative. Minus 4, that's minus 64. 16 times 2 is 36 plus 36. So that's 14, 5. That's 8. 2 minus 28 minus 9. So that's minus 19. Minus 19. Okay. This is minus 3. That's minus 27. 9 times 2 is 18. Minus 9. So that's 27 minus 9 plus 9 minus 27. Okay, so that's 17. That's 8. 6. That's minus 18. Okay, you know what? I probably should be using a calculator because my math right now is not too great. All right, so we're going to do 4. Okay, minus 64. Here, 16 times 2. That's where I went wrong. Minus 64 minus 9. That's minus 41. This minus 3. Okay, minus 27. Minus 18. Okay, so minus 9, minus 9. Let's see. That's minus 27 plus 18. Okay, that should be minus 9. Minus 9, so that's minus 18. How can we get minus 18 at both spots? Let's see what I screwed up. This is minus 27, 18, 9. That's minus, okay, so that's right. Okay, now let's do the 2. Okay, that's 8 minus 8 plus 8 minus 9. This one is minus 1 plus 2 minus 9. Okay, so that's minus 8. And now we got 0. That's minus 9. And 1 plus 2 is 3 minus 6. 2 is 8. 8 plus 8 minus 9. So that's 16 minus 9. That's 7. 27. 9, 18. Minus 9, so that's 27 plus 9, 36. And one more, and that is 64. 16 times 2 is 32. 6, 9 minus 9, that's like 80, what, 7? Yeah. 87. So that's a big number. This function goes up fast. And if we plotted it on an XY coordinate, I don't know how well we could do that here. Just picking functions arbitrarily. 1, 2, 3, 4. 1, 2, 3, 4. And we must have a 0 somewhere. So we got 1, 2, 3, 4. You can see that plotting by points is awkward. So at minus 4, we're way off the chart down here. At minus 1, we're, let's say if this was 2, 4, 6, 8, minus 8. So at minus 1, we're down here. At 0, we're down here at minus 9. And let's see, at minus 2, we're at minus 9. So we're doing something like this. And at 2, we're at 7. 2, 4, 6, 8. So 7's there. 2, 7. So we go up pretty sharply. So we're at 7 there. So we go up pretty steeply. This curve doesn't make that. There we go. So we have sort of a curve that does this and goes up quickly, goes down quickly. But we're just assuming that, you know, we don't know for sure. We don't know the 0 exactly, but we presume that there's a 0 here. We know that for all the positive numbers, 6, 7, all that, this is going to be positive, so it's going to be way off the chart. But, you know, we don't know much about where this turns, where it becomes 0. So derivatives help us a lot more than just trying to plot on tables. Tables can be a little bit cumbersome. So we've got y equals this. So let's, y prime equals 3x squared plus 4x. Okay, so we can factor this out. If we set y prime equals to 0, equals 3x squared plus 4x. If we factor this, we got 3x plus 4 and x times x. Well, this is 0 when x equals 0 and when x equals minus, let's see, 3x plus 4 equals 0. X equals minus 4/3. So x equals minus 4/3. So at those 2 points, the derivative is 0. So x equals minus 4/3 and 0. So these are maximum and minimum points. Okay, so that's our minimum. That's what setting the prime to 0 gives us maximum and minima. Okay, so these are local maximum and the local minimum right there. So at x equals 0, we got a local minimum, and x equals minus 4/3, we have a maximum, a local maximum before the curve takes a turn down and then back up again. And if we do y double prime, we can look at inflection points. Inflection points is where the curvature begins to change. You can see here you got a curve going that way. Down here we have the curve going this way. So those points right there are where the curve changes. It's called an inflection point. And the double prime, or the second derivative, gives us the inflection point. So we have 3 times 2 is 6, x plus 4 equals 0. So we have an inflection point at x equals minus 4, 6. So right there at that point, at minus 4, 6, that's minus 2/3. We have an inflection point. That's where this changes. So we have a local maximum, a local minimum, and the inflection point where they occur. So we get information about the plot that helps us, and we're assuming, because this is a polynomial, that it's continuous on the entire domain of the real numbers, negative all the way negative infinity to positive infinity. What we're interested in, what we're mainly interested in, is the behavior of the function at where it does something. And this is where it does something, right here. Everywhere else, it just goes up or it goes down. And it doesn't do anything interesting. It's only in this point here where it does something interesting. And these derivatives, the first derivative and the second derivative, help us to find out where that interesting behavior takes place on a given curve. And so that's why we use derivatives to help us plot functions. So this is a fascinating aspect of derivatives, and it's also one of the first things that you learn when you take a course in calculus. is how do derivatives help you plot functions? And the two key things are, where are the local maximum and minimum? And where are the inflection points? Where does the curve begin to make its changes? And when you look at that, what you see is that when you plot, let's say, values before this, the inflection points are going to be negative. All the numbers or all the values on the negative side of minus 2/3 will be negative, but on the right of minus 2/3, the values of that second derivative are going to be positive. And that tells you that you've had a change in the direction of the curve, the inflection point. And that is one of the key or important aspects of plotting a curve and to find out where that change takes place. So let's take a look. Something a little smaller than 2/3. So let's look at 0. So when x is 0, y double prime is equal to is equal to 4 plus 4. And you can see it was positive. If we chose -1, we have double prime equals -6 plus 4 is -2. So on this side of minus 2/3, we see that the values are negative. On this side of minus 2/3, the values are positive. And that tells us that at minus 2/3, we have an inflection point. And all an inflection point is the point at which the curve changes direction. And knowing whether it's negative or positive before and after the inflection point tells you which way the curve is changing. So here we've got our local maxima and minima. We've got our inflection point. And so we know that this plot, as we've got it here, is pretty accurate, even if I did draw it kind of sloppily. I'm not a very good artist. So I think those points are pretty well understood, hopefully. We'll be doing more of this. I just arbitrarily picked a function. I didn't know what its behavior was going to be, but it turned out to be pretty good. And I'm also drawing back from memories that are very old. I haven't done this stuff in a long, long time. No, not even at work. So this is how we use calculus to help us plot. All right, so that's kind of the curve that we've got there, and I did mess it up a bit, but there we go. So there you go. I could do this in Excel and you could see it better, and I might just do that. So anyway, we'll look at this more. I'm just introducing this to you, how derivatives help us. We just don't do them for no reason. They provide a lot of information. Like I said, they can be looked at in a physical way as being the velocity and acceleration. The first derivative is the velocity. The second derivative is the acceleration of the function. Or we can use it to help us plot by finding the local maxima and local minima and the inflection point, the point where the curve changes direction. So I think we've bitten off an awful lot at this point. We did a lot of derivatives, and now we're looking at using derivatives as a tool to help us understand the behavior of functions. And looking at and the behavior of functions is called analysis. So when you hear a mathematician talking about analysis or calculus and analysis or geometric analysis, this is the stuff that they're talking about. So anyway, we'll take a look more at this in the next couple of videos, and hopefully it'll be interesting and fun. And again, we'll look at this more detail. So take care and be safe. Don't be foolish with the coronavirus.